Okay, so we're up. So we're the last week. We got 2 days left. I've got about half the exams from the previous one graded, so I'm a little bit behind there. And I was going through Canvas messages until the end of Tuesday, and then there's a whole backlog of those now. So if you're waiting on a Canvas message reply, I apologize. We'll get those going. Okay, we got one last topic though, so it has to do with quaternions. So it's chapter 12. For what we wanted to accomplish in class, we really didn't have to do this at all because we accomplished what we wanted. Forward reverse analysis of position problem of spatial manipulators. Did a lot of stuff. Saw that depending on the geometry, sometimes the reverse analysis is pretty darn easy, based on the toolbox that we built up. And then sometimes those group 3s and 4s were just terrible unless you had special geometry. So we kind of covered all those. Okay, for quaternions. So why are we doing it? It's another way to represent orientation. You say, well, do we really need one? It has a couple of advantages to it, so that's what we're going to see. So, if we think about how to represent orientation, what do we have so far? We could say, of course, the old problem, how, B is aligned with A. And we had a general problem, was rotate some angle theta about some unit vector m. That had to be a unit vector, or we unitize it. And we were able to come up with the general rotation matrix. So you can say this is one way to represent the rotation. Oh, my computer's flipping out. There we go. Of course, in the rotation matrix, the other way we did it, we knew that this first column had to be the vector along the B coordinate system measured in the A. So if we looked at it, we knew how to get from here to here, but this is 9 numbers. It's okay, but 9 numbers under 6 constraints. The columns are unit vectors and they're perpendicular to each other. And you look at this and you say, well, this is 4 numbers, theta and m. Oh, another way to do orientation. B is aligned with A. We could do, they call them Euler angles. You could rotate some angle theta about, the x, followed by rotate some gamma about, the y-axis. And then again, we could rotate some angle, I don't know, beta about the z. And you say, well, that looks really good because it's only 3 numbers. So we're just trying to come up with ways to represent it. Turns out quaternions are going to be useful, and quaternions are 4 numbers. So what are the advantages, disadvantages of any of these? So, first, this is a little bit cumbersome because you have the 9 numbers out there. This one looks pretty attractive because it's only 3 numbers, but we're going to see that there's one kind of significant problem with it. And I'm going to show an example that I've got in SolidWorks. Okay, so this, oh great, it has encountered a problem, needs to close. Aren't you nice? I had it all set up, ready to go. Okay, we'll close so I can reopen you. Come on. Close, close, close. I don't need a crash report. So here I thought I was, oh, looks like it closed. No, it's still thinking about it. What is it mad at? Oh, done. Oh, we are glad for that. Okay, we're going to open that back up. So again, we're trying to look at these different ways to represent orientation and come up with some kind of motivation of why quaternions can be handy. Okay, so I'm going to open this one up. This is they call them Euler angles, for example. What I've got there, rotate about the x and the y and the z. Okay, rebuild. So you can see there's a fixed coordinate system. The x is that way, and the z is straight up. I guess I did not draw it. And this other coordinate system, I moved it up here because I thought it would be easier to see, but I don't want to move the origin, so it should be down below. But we're going to rotate some angle about the x, followed by, the new y now is up that way. So we're going to do some angle about the y, and then finally, let's go ahead and lock that down, and then some angle about the z. So you say, it looks pretty good to describe the orientation. So why, not go with that? Well, there's one example here that is a real problem. I got to go ahead and float that. Suppose the second angle is such that that happens. Oh my goodness. So now I could rotate about, oh yeah, here I am rotating about the X. And then the third rotation is kind of like it's automatically, somehow it's being smart here and it's counteracting it. Because notice how the orientation's not changing. So for that orientation, the problem we got here is that there's more than one set of beta, gamma, betas that gets you the same orientation. We really don't want every orientation to have more than one name, right? We'd like to have one set of numbers for that. So this is a problem, these special ones like that, when that happened. And again, it only happened when that green one there, the second angle, right? The first angle was that, the second angle, when the second angle lines that up like that. So because of that, a lot of times people like to use the word singularity again, but because of that case, that Euler angle thing looks a little bit dangerous. And then we come back and we look at the board and you say, well, this looks pretty good because it's 4 numbers. And then when we look at the quaternion, it's going to be 4 numbers, right? Because you say I'm going to rotate about some vector m, by an angle theta. And the only issue with that one that I'm not really thrilled about is I'll get the same orientation if I go negative theta about a negative m vector. It's not terrible, but still, that means that every orientation relationship has 2 sets of 4 numbers. So I don't really like that. So it's going to be nice with the quaternion is every orientation is going to have 4 numbers. And they're not going to, have 2 possibilities and all that kind of stuff. So that's what's good about the quaternions. Oh, another one I want to show is a lot of times when we're building up systems, whether they're manipulators or autonomous vehicles and all, we have multiple processes running on the computer and they intercommunicate with the processes, send data to each other using what's called ROS, the robotic operating system. And if we go to ROS, so I went to Google and said ROS to geometry messages and this came up and I'm going to look in here. These are pre-written messages that are used quite often. And let's take a look at what they use for pose. So a pose is going to have a variable in the message of type point, and I can click here and see what point is. Oh, it's got an X, a Y, and a Z. And the name of that field in that message is called position. And then it also has, to define the orientation, because a pose is a position orientation, it has a quaternion, the name of its orientation. And when I go to quaternion, it's got, they call it XYZW, we're going to call it D and ABC. But it's got these 4 numbers. So it's used a lot. I know it's used in space applications and all kinds of things. So because of all that, Dr. Duffy thought that we should put a chapter in here on quaternions, and we're going to do it in 2 days, cover what you really need to know about quaternions. Okay. Hey, while I'm here, I just noticed I had this up. I was supposed to do this during the administrative thing, but like when is our test? I hadn't looked it up till today. But if you go for final exams UF and you look for the fall schedule and you come down and you're looking for second period Monday, Wednesday, Friday, and it turns out to be, here we go, 10 a.m. to 12 till noon on Thursday the 12th. So I'll get that put together. I'm a little nervous because I have 22 messages in my Canvas inbox today. And if I get any more special cases, I'm going to hit my head against the wall. Special cases of, well, I already bought a ticket to go to what, this thing's been published for a year, so, okay, but we'll deal with that one later. Okay, so we're back to quaternions. We said the motivation was the fact that we're going to be able to come up with 4 numbers to represent every orientation, and every possible orientation only has 1 set of 4 numbers. So if we look at the definition of quaternion, sometimes this stuff kind of cracks me up or drives me nuts either way, but it's kind of a correct definition. I want to make sure I get it right here. So it says, what's the definition of a quaternion? So they'll have these mathematical kind of definitions that are totally correct, but they don't tell you anything. So a real quaternion, so that means we're going to have real numbers, not complex numbers, is defined as a set of 4 real numbers written in a definite order. And that's it. 4 real numbers. So we're going to say I could have a quaternion Q. I'm going to call it Q1. And it's going to be 4 numbers. D1, A1, B1, and C1. Now again, when we looked at that Ross thing, they called them XYZW. The XYZ is our ABC, and I think what they call W is our D. So it doesn't really tell us much. It just says 4 real numbers. So an example of a quaternion could be, Q1 might be 3.2, negative 1.8, 4.7, and 2.3. You say, well, whoopee, right? What does it really do for you? So what we're going to start off with before we show how this is applied to orientation is we're just going to learn about quaternion math, like what happens if I have 2 quaternions and you add them together, subtract them, multiply them, and can you divide them? So it's a little bit like what we did when we did the dual numbers, the epsilon thing. We're just going to go ahead and do all these definitions. So what we're going to start off with is, suppose I've got 2 quaternions, so I'll have a D2 and A2 and a B2 and a C2. And if we were to add those together, there's not going to be anything terrible here. D1 plus D2 will be that component. This is just going to be A1 plus A2, B1 plus B2, and C1 plus C2. So nothing too magical. And if we subtracted Q1 minus Q2, right, they'll just have minus signs in there. So there's nothing really, crazy. Of course, we don't see why are we doing this yet, or how does this work and all. Suppose I had a quaternion Q1, and I multiplied it by some scalar lambda. So for example, if I had, so lambda might be like 5.2, and Q1 is whatever numbers. Well, it's going to be pretty easy. It's going to be lambda times D1, and lambda times A1. And lambda times B1 and lambda times C1. So nothing too magical there, nothing too bad. Oh, if we do have a 0 quaternion, it means that all 4 numbers have to be 0. So nothing too bad. So now we're going to look at a couple of ones where I think I'm going to put these on the screen instead of writing these all on the board. There's some other quaternion algebra stuff that's kind of obvious, I guess. So I'm gonna, here we go, this section right in here. So we've got, based on our definition for addition, it doesn't matter about the order. P and Q are quaternions, and in this case, lambda and mu are scalars. Again, if I have 3 of them being added, you can kind of tell from our definition it doesn't matter what order you add them in. If I have a scalar, lambda times a quaternion, I could have post-multiplied and still had the same result. Here's 2 scalars. In other words, I could multiply those scalars together first and then multiply by Q, or I could do this multiplication first and, So these are, hopefully these are kind of obvious, so that's why I just didn't feel like writing them on the board. And that one down there. So what's left, though, is quaternion multiplication. And quaternion multiplication has a long story to it. So to begin with, we went ahead and, this fellow Hamilton is credited with what we're going to do here with multiplication. Went ahead and defined some special quaternions. So the quaternion 1 is going to be 1, 0, 0, 0. The quaternion I is going to be 0, 1, 0, 0. The quaternion J is going to be 0, 0, 1, 0. And the quaternion K is going to be 0, 0, 0, 1. And boy, they kind of look a lot like, we're used to IJK for vectors, but we're not doing vectors right now. These are quaternions, IJK. So if I wanted to take this quaternion, I could write it, as these 4 numbers, or I could write it as D1 times the quaternion 1 plus A1 times the quaternion I, B1 times J, C1 times K. And we'll probably use this notation a lot more than we will just write down the 4 numbers. Okay. And the other thing that's maybe a little bit ironic because, right, these look like vectors, but they're not vectors, but here we're going to use the word vectors. A lot of times for the quaternion, we'll call that the scalar part. And we'll call that the vector part. I get nervous about this because it's not a vector, it's a quaternion. So why do you call it? Well, we're calling it that because it kind of looks like it, I guess. So it seems kind of strange. Okay, so now that we've got that, we have to go ahead and define multiplication, and this all comes down to this fellow Hamilton. Okay, so Q1, Q2. So I've got those two quaternions. I could write them like that. So I could say the product Q1 times Q2 is going to be equal to D1 times quaternion 1 plus A1I plus B1J plus C1K times, D2 times 1 plus A2I plus B2J plus C2K. And this multiplication is going to be real important for us, this definition that comes out. And to start off, we're not going to do anything magical. We're going to say it's equal to D1 times 1, right, times D2 times 1. Boy, there's going to be a lot of terms. Is it 16, if I got this right? But we're just going to go for it. So I've got plus, D1 times quaternion 1 times A2I plus D1 quaternion 1 times B2J plus D1 quaternion 1 times C2K. And then I've got A1I times D2 quaternion 1 plus so we're not doing anything magic, right? We're just, so A1I times A2I plus A1I times P2J plus A1I times C2K. Oh man, this is getting tedious here. B1 times J times D2 times 1, J times A2 times I. Let's see. Yeah, this is pretty tedious. I should have had this typed out in PowerPoint, then I wouldn't have to write it on the board. B1, C2K, and I guess we got one more term, so we're almost there. C1 times K times that, C1K times that. So on this part, there's no, magical new kind of multiplication type rules or anything. Oh, I forgot something here, a J. So we just multiplied them all out. We got all these terms. But the issue we have then is, what's the definition if I have quaternion 1 times quaternion 1? What is it? And here's quaternion 1 times I, and 1 times J, and here's I times I, and I times J, and I times... What are all those definitions? So that's the part that falls to this fellow Hamilton. He came up with a set of definitions that was going to allow quaternions to actually be able to do things. So we're going to take a little bit of look at history here of where this came from. So if we go back to our website and we go to, not there, there we go. And we go down to notes, we go down to chapter 12. So this is the fellow. So 1805 to 1865, so it's been a bit of a while. I got a picture of him here. And, this is kind of an interesting website. It has a lot of his history and biography. Oh, look, here's a whole section on quaternions. He did other things also. Lectures delivered, holy cow. So I guess they didn't have Edge back then, so they wrote it all down and put it out there. So we can take a look at that, but there's kind of another one that I want to look at, this letter on quaternions. This is a letter that he wrote. He said he passed away in 1865, so it was near the end of his life, and he wrote it to his son. And he's telling him kind of the history of how he came up with this multiplication. So we're just going to take a look at just a little bit of this. But his son Archibald, he said, I've been wishing for occasion to correspond with you about quaternions. And you mentioned in your note yesterday about reflecting on several points, particularly the multiplication. He called it multiplication of vectors, because we had those vector parts. You can't multiply vectors. I mean, what the heck? And then he says to his son, he says, no more important or indeed fundamental a question is there in the whole theory of quaternions. What is multiplication? What are its rules and its results? Are there any analogies to other things, like vector operations? And finally, what good is it? Turns out for this orientation stuff, man, they are super. Okay, so he's going to tell the story here. So again, he passed away in 65, so this was, what, 20-some years ahead of time? Let's see, what's he about? He's talking about it, the year and the month. While having returned from visits that I were connected with a meeting of the British Association, the desire to discover the laws of multiplication, he's going on and on and on. Every morning, oh, this is funny, every morning in the early part of the above month and coming down to breakfast, you and your little brother would say, well, Papa, can you multiply triplets? Whereas I was always obliged to reply, no, I can only add and subtract them. So my kids were not quite into it, I guess, enough to ask, have you solved the reverse analysis of every morning? No. Okay. But on the 16th day of the same month, it happened to be a Monday, and okay, he's going to the Irish Academy. He was walking to 10. Mother was walking along the Royal Canal. Okay, and she talked to me now and then. So obviously he was not paying attention, right? He's just out walking, and he's thinking about multiplication. An undercurrent of thought was going on in yeah, he was not paying attention, which gives, at last he got the result. If not too much to say, I felt once the importance. So he came up with these definitions of multiplication of quaternions, and he even knew that, oh yeah, this is it. An electric circuit seemed to close and a spark flashed forth. I foresaw immediately of many long years to come of work to do on this. Let's see. Now I couldn't resist to cut with a knife. He was crossing this bridge, on the Brum Bridge. As we passed it, the fundamental formula with the symbols IJK. That was the foundation of his definition of multiplication. We're going to see how it works out. From that, everything came. And it goes kind of on and on. And I guess, I don't know if I'll ever get to go to, what town was this? In Ireland. Quaternion Bridge. Oh yeah, okay. You can't do that right now. So here's this bridge for nearly the famous for being the location where Sir Hamilton first wrote down the fundamental formula. And there's a plaque now, so I guess this part that he carved isn't there anymore, but they have a plaque. Here as he walked, a flash of genius, the fundamental formula is cut on a stone on this. Oh, and here's the plaque. Holy cow, even the plaque looks old. So, I don't know, I just thought that was kind of a neat story. Because, I mean, it kind of makes things a little human. He's walking along, and he's not listening, and then he thought of this, and he wrote it down on the bridge. Okay, so all of his definitions really spun from that. So on the bridge, he had I times I is -1, J times J is -1, K times K is, and then what was IJK? I think IJK was 1. Oh, IJK is -1. So, okay, so let's go ahead and write down what they all are. So all of the rules for multiplication. If I have the quaternion 1 times the quaternion 1, it's going to be the quaternion 1. If I have I times I, it's going to be -1, J times J, K times K. So we got that. Let's see, I times J is going to equal the quaternion K. I'm going to cheat here. It kind of matches the cross product rules. Oh, but if I have J times I, it's going to be -K. And again, these aren't vectors and stuff, but I kind of wrote what I did when I do cross products on vectors, because that's how I remember the quaternion rules. K, J times K is going to be I, and K times J is -I. And then what's the last one? K times I is going to be J, and I times K is going to be -J. And there's got to be something I forgot here. Is that all of them? That might be all of them. Oh, 1 times I is I, and 1 times J is J, and 1 times K. I times 1 is I. So those are all the rules. So to me, it was kind of wild that he knew that that was going to allow him to do a lot of neat stuff. We're going to apply those rules, though, to what we have over here. Okay, these are scalars. So scalars can, like lambda and mu that we had, right? They can move up front, right? The order didn't matter. So now I've got 1 times 1, and 1 times 1 quaternion is the quaternion 1. 1 times, again, the A2 could move up here because it's a scalar. 1 times I is I, 1 times J is J. Okay. I times 1 is I, so I'm going to move the D2 up there. I times I was -1. Oh, I guess I should put the 1 quaternion. But we're also going to find that with the 1 quaternion, half the time I'm not going to even write it down, because the 1 quaternion is the quaternion associated with the scalar part, and the ijk with the vector part. Okay, I times j was k. I times k is -j. According to Hamilton here, j times 1 is j. J times I is -k. J times j is -1. J times k is I. Okay, k times 1 is k. K times I is heaven, j. I was going to say heaven knows. It had to be a j, just plus or minus. K times j is -I. And k times k is, what, -1. And now we're just going to regroup this together. We're going to write it down. So I'm going to get rid of some of the stuff over here. We're going to put the results. So first thing I'm going to do is group all the scalar parts together, right? All the terms up there that have the quaternion 1. So I'm going to say Q1, Q2 has, quaternion 1 times D1, D2. And I'm going to cross these out as we go. So we got that, we got that, we got that, and we got that. So it's minus A1, A2 minus B1, B2 minus C1, C2. So, okay. Now I'm gonna go ahead and group these a little bit different. I'm going to take these 3 terms and write those down next. So I'm going to say plus D1 times A2I plus B2J plus C2K. I'm just going to group them different, but it's the same. Because at first you would have said, well, how come I don't group all the stuff with I? And then, yeah, you could. But that took care of those terms. I'm going to take these terms next. So I'm going to go plus D2 times A1I plus B1J plus C1K. And then I wish I had a little more board space here because I'm going to need a little bit of room. Because if we look at what's left, right, those 3 are crossed out. I'm going to write this down, and then we're going to see if it's not correct. I'm going to put a determinant down here. I wish I had more room. Okay, it shows up on the screen. And up top here, I'm going to put the quaternions, I, J, K. And then here, I'm going to put the vector part of the first one. And here, I'm going to put the vector part of the second one. And then we're going to see if we expand this determinant, do we get all those terms that are missing over there. So there will be I times B1, C2 minus B2, C1. There's an I, yeah. Yep, B1, C2 minus, yep. Okay, and then the, well, let's do the K. K times A1, B2 minus A2, B1. Here's the minus A2, B1. And where was the other K? Okay, and then for the J term, there's a minus sign, so it's A2, C1. A2, C1. Minus, yep. So I got all the terms, I just kind of grouped them differently. And then this is the way that I kind of remember it, that if I take 2 quaternions, whatever these numbers are, they're real numbers, I get a quaternion because there's going to be something times 1, there's going to be a bunch of stuff times I, which I could have grouped together, but it's just kind of convenient to write it this way. And there's a bunch of stuff times j and some bunch of stuff times k. And so the easier way to remember it is, though, is we have this scalar part up here. I just have to remember the minus signs. And then there's the scalar part of the first one times the vector part of the second, scalar part of the second times the vector part of the first, and then this crazy determinant, which I can remember. It's ijk, and then it's the vector part of the first, vector part of the second. So if you gave me numbers for D1, A1, yeah, I'm going to get a quaternion, and it's no big deal to work it out. But the only thing that's funny here is there's a whole bunch of stuff in his definitions that are pretty cool. You know, one is like I times I is -1, and j times, you know, j is -1, and wow, this kind of looks like a cross product of vectors. And so it looks like this quaternion stuff might be able to include a lot of the stuff that we're used to with vector type things. But that's the definition. Okay, so the first one is when you look at this, does the order matter? Does that equal, right, does the order matter? And it does matter, because if I switch the order, these two rows are going to switch. Because, right, the Q1, Q2, so the second row was the vector part of the first quaternion, and now it's going to be the vector part of the second quaternion, because that's the first one in the order of that multiplication. So the order matters. Sometimes, I know in the book there was a question that says, what would have to happen in order for Q1, Q2 to equal Q2, Q1? Oh, well, the vector parts have to be like parallel to each other is what will happen. So when you switch the order, in other words, this determinant goes to 0 is what the special case is. So that's the answer to that one. So, because yeah, if this determinant goes to 0, kind of Q1, Q2, well, it'll still be 0 when it's Q2, Q1. So that's kind of the special case. The vector parts are where you could say they're linearly dependent, but in this case, they have to be parallel. So that's our definition of multiplication. You say, oh, wazzer. So isn't that fun? How do I remember that? Well, I remember what we wrote down there because of this format we're in. We're going to take one look at some stuff. I got to check the clock here. That's on our website. And again, there's always a quaternion question on the test. It's open book. It's open notes. I got a couple of things out here. Here's a spreadsheet. So we'll open this up. Where the yellow stuff is, that's where you can type things in. I wish I had, I guess I'll be okay. I said I wish I was in pure Excel and not in the, this web page thing. But, so what we've got here is, there's sort of three things that are shown here. So the first one is, if I was given two quaternions, Q1 and Q2, here's the product. So this is just calculating the scalar part and the ijk of, let's see if it updates. So I'll put a 3. Yep. Oh, it's read only. It says doesn't agree. I should have downloaded it. Oh, I don't want to do any of this. Come on. I just want to find. I'm going to say download. Save link as, and I'm just going to throw it in temp so I can mess with it. Open it in Excel. So, I wish there was like quaternion stuff on my little calculator or whatever, but no, but this is kind of like the calculator. So is it still mad? Enable editing. Okay. So if I change this, as we go bigger, oh, come on. Okay, let's put that as a 5 and a 0 and a 2 and a whatever, and you can see how it's updating. And all this is doing is these, oh, look at, like this cell here is just that D1, D2 minus A1, A2 minus A2. So this is a little calculator for you that you're free to use that. The other stuff that we won't get to until Wednesday, but we're going to show how the quaternion can be used to imagine we had a body and it rotated to this new position, rotated about some vector m by the angle theta. Oh, look, here's the angle and here's the vector. Now it needs to be a unit vector, but what my code does is this is where it unitized whatever you put in. And this is the particular point, and this is where it wound up after that rotation. So you can take any point so we're gonna look at that on Wednesday. And what's this one do? It says, hey, if you're given a unit quaternion, and we're gonna find that a unit quaternion is one that if you take the square of all four of those numbers and sum them up and you get 1. Every unit quaternion represents an orientation. So if I had a unit quaternion, I would love to be able to find the angle and the axis. So those are in the spreadsheet. Also, what's out here is if you want to mess with Maple. Oh, I thought I had a PDF here. Because for me, we'll do this one on Wednesday. I'll open it up. For me to fire this up, I have to go to UF Apps and open Maple. And I thought I had a PDF of it there, but I do not see it. Oh, and this one, the link is dead. I don't have the solution to the book problems. So there's some stuff out there that you can use. Okay, so what do we got to do with this today? We've got 15 minutes, and we got a little bit of stuff left to do. So we need to go to this. Oh, and there's all those definitions. Okay. Oh, so this is like the thing I wrote on the board. So that's the important definition. Again, we have the scalar and vector parts, nothing new there. And, oh, we do show it here, although to me it's not all that important. What if I had two quaternions that had no scalar part? So the D was 0. So all I have is the vector parts. So I guess that's, remember when he said his kids were asking, could you multiply vectors? Well, if you just had quaternions with no scalar part, this is just that equation, right? The D1, D2 went to 0, so that's 0. So you get, what, negative, that's just that general equation. It's not that important to us. Oh, but it is kind of neat. The scalar part is equal to the negative of the, so if you took two vectors and scalar, quaternions with no scalar part, and you multiplied them, the scalar part becomes the negative of the dot product of those vectors, and the vector part becomes the cross product of those vectors. So it's like, holy cow, that's kind of weird that that happened. So these are the ones that I didn't feel like writing on the board. So again, the order matters, but it doesn't matter if I do PQ, then R, or if I do QR and then pre-multiply by P. And then this is going to hold true for us. So these are all quaternions, PQ and R, so I just didn't feel like writing those on the board. Okay, so what we're going to do next is, we haven't done division, so that's where we have to head to, and we got 13 minutes to get to division. So I'm going to leave that. I'm going to get rid of this. And we can get rid of all this. So to define division, it's not normal division. What we're going to wind up is defining the inverse of a quaternion, like 1 over Q. Okay, so the first thing we're going to introduce is called the conjugate of Q. So if Q1 is, well, let's write it this way. D1 times 1, A1I, B1J, C1K. The conjugate, we're going to write it like that, of Q1 is you negate the vector part. You say, okay, well, whoopee. So we negate the vector part, so that gets us that. Okay, what happens if we were to take the original quaternion Q1 and multiply it? I'm going to put it in parentheses just to remind us that that's the conjugate. It's not like some K times Q1. If you were to do that multiplication and we go ahead and we substitute over here and we look at it and we look at it and we say, okay, the vector part got negated, so right, I would have D1 times D1, right, because the conjugate, and oh, this would go, what, to a positive now, right, because the vector part got negated, so the A2 would be negative A1. Oh, so it looks like what we're going to get is, for the scalar part is I put the 1, that's okay. D1 squared plus A1 squared plus B1 squared plus C1 squared. And then over here, you know, I've got, and that's going to be negative A1, negative B1. That's going to be D1. Those are going to cancel. And down here, I got A1, B1, C1, negative A1, negative B1, negative C1. That determinant's going to 0, so that's it. So if we take a quaternion and multiply it by its conjugate, we're going to get, right, I should have put times 1, but a lot of times we just don't even write down the 1. I'm going to get the scalar part. I'm going to get the scalar term. You say, okay. Well, again, for now, it's like, well, a big deal, what that's going to get us. We're going to call this scalar thing over here the norm of Q. And what we're going to find is any quaternion whose norm equals 1 can be used to represent the orientation relationship of two coordinate systems. So that's what's coming on Wednesday. And we're going to do it by brute force on Wednesday. Okay, conjugate, okay. Oh, so here's one we're going to do. Let's see, I want to make sure I don't mess this up because I got 10 minutes. Because I kind of know where I wanted to get to today. I just got to make sure we can get there. Okay. Okay. So any quaternion times its conjugate just gets you a scalar, a norm value. So what we're going to do now is take two quaternions. So the second one, right, is D2, A2, and I'm going to let Q equal the product Q1 times Q2, and the order matters, and we know what that is. It's over here on the other board. And I want to get the conjugate of that. So the conjugate of that says, well, this is what I get when I multiply it out. I just have to negate the vector part. So I'm going to get a negative sign here, a negative sign here, and a negative sign here. And I'm debating, do I want to just do that? Q1 times Q2, oh, the conjugate, oh, dang it. I'm trying to figure out how to get there with the minimal use of chalk. So the conjugate of that product is, right, negative, negative, negative. If I swap the rows here, that becomes a positive. If I multiply this row by -1 and this row by -1, it's still good. And if we look at this result that's out here, so this is the conjugate of the product, and the product was on the board. I just, mucked it all up. And if I look at this, it's going to wind up, what if I was to do that multiplication? If I was to take, I'm going to do it in this order, though. So Q, again, was Q1 times Q2, and this was the conjugate of that product. Turns out this is going to be true, so let's double check it. I don't think there's any change here. I'm going to have the scalar part of that times the vector part of that. Oh, I'm trying to show that this is going to be equivalent here. Okay, well, this conjugate, I got to be careful, is D2 minus A2I minus A2J minus, B2J minus C2K. And this one was D1 minus A1I minus A2J, oh, I'm doing it again, B2 C2K. If I take these conjugates, and here's what those conjugates are, and I do that product, I should get this, right? I get D2, and because of the minus and the minus, am I still okay here? Yeah, I times I was -1, so yep. And then we're going to have this scalar part times, so I have a plus out here, but I'd have minuses there, so that's okay. And then I got this scalar part. Well, I would have had minuses there, so I pulled the minus out. And then, yeah, I have, right, this is first in the multiplication, so it goes to that. So, okay, so what we're trying to get to here was just a little thing to tuck away if we ever need it. if I have a quaternion, which is the product, like Q1 times Q2, the conjugate of that Q is the conjugates of the things that form the product multiplied in the opposite order. So it's just a little tidbit. And what if I go ahead and look at the norm of Q now? The norm of Q is going to turn out to be I guess the same as the norm of the conjugate of Q. Because remember how the norm was the d squared plus a squared plus b squared plus c squared. So yeah, on the conjugate, the ABCs are negative, but they're squared, so it all works out. So there's just two little tidbits that are out there, and then we got 5 minutes left, and we have to get to division. Okay, the conjugate of Q is the product of the conjugates in opposite order, blah, 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 blah. Okay, quaternion division. So the norm of Q is equal to Q, KQ. So Q is just any quaternion. What if I switch the order here? If I switch the order, do I get the same result? And you will. And again, I wish I was debating about should I overwrite the general multiplication rules. It was so handy to have them here. But if we check that out, the order doesn't matter when the Q times its conjugate, because you're still going to get d squared plus a squared plus b squared plus c squared. So we could look at this and say, this is a scalar like lambda. So I can multiply, quaternions by scalars. So what if I multiply by the scalar 1 over lambda? Yeah, fine. So I can say that 1 is equal to Q So here's something. This is going to be a quaternion because I just, my lambda happened to be 1 over that norm value. That when I multiply a quaternion by this thing, I get 1. So we're going to call this thing Q inverse. So we don't really have division, but we have inverses. So how we're going to use this is, suppose I had some quaternion equation that said, make sure I get this right here. Okay, R1 times Q. Okay, and I'm going to say I'm given the two quaternions Q and P, and I'm trying to solve for R1. So I'm going to take R1, Q inverse, and Q inverse is going to be 1. And again, the Q inverse is the conjugate of Q divided by the norm of Q. So that's how we're going to use this. I'm just going to write it like this, though. It's Q inverse. So we don't really have a division, so to speak, where I can't really say P over Q. But I have an inverse, so I can use it like that. So if I had an equation, I knew Q and P as quaternions, and I'm looking for this one. Yeah. Okay, what if we had a thing that said Q equals, how about Q R2 equals P? So how do I solve for R2? I need to pre-multiply both sides by Q inverse. So I'm going to have R2 is equal to Q inverse times P. So we have to use it sort of like we use inverses with matrices where it's the left side and the right side, it all matters. We just have to keep track of it like that. So that's our definition of division, so that's not too bad. Okay, so the one last thing we have is, we got 2 minutes, so I'm just going to buzz through this. So I'm getting through to 12.5 in the book. So 12.6 is rigid body rotation. That's where we're going to show how quaternions can be used to represent orientations. The last thing we show in the book, and I'm just going to write it out, is suppose we had Q was equal to some Q1 times Q2 times Q3, like a whole bunch of them, and I want to come up with Q inverse. So it turns out that it's going to equal, I'm just going to go with these three here. It's going to be these written in opposite order. And I don't want to say the proof is in the book, but really quick, where did that come from? We know Q inverse has to be, I'm trying to do the proof really quick in my head here without looking at the book, and I'm going to mess it up here. I'm going to mess it up if I don't peek. Okay. The inverse of Q may be written as, oh, I don't even have a proof in the book. It says the inverse can be written as, oh, we know how the conjugate of Q would be the conjugates in opposite order. The norm is a scalar, so it doesn't matter about the order of that. So I could say the conjugate of Q is what Q, so that's what I'm trying to prove. So again, we already showed how it was the conjugates in opposite order. And if we go ahead and, oh, the norm of Q was the product. Didn't matter the order, Q1, norm of Q2, norm of Q3. So if I take this conjugate of Q and divide it by the norm of Q, so I take this divided by that, I can put this under that, and this under that, and this under that. KQ over that is that. So what we're leading up to is, in case we ever need it, if I have not just Q as a multiproduct of a couple of quaternions, but if it was a whole bunch of quaternions, I know that the inverse of Q is that inverse, in case we ever need it, and we might need it on Wednesday. So that's what we're trying to show there. So we haven't done, we're into overtime. We haven't done a ton today, but just kind of introducing you to a new concept. And so like, don't fret today, right? It's like, yeah, okay, these are the rules. It's kind of neat that this guy carved it, I thought, in the bridge. I thought that was neat. Plus the part about, he made it so human about how he's walking with his wife and blah, 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 and all that story. Came up with this definition, and so far we're just doing things with his definition, but on Wednesday we're going to show how we can use quaternions to represent rotations or the orientation relationship between two bodies. And it's used a bunch. And the advantage is that, again, a quaternion is 4 numbers. Every possible orientation of B to A has one quaternion that'll define it, which is the advantage of it. You don't have, this orientation has 2 names. Remember, like we had M and theta? And you say, well, I go negative M, negative theta, and I got the same. Yeah, I don't even want to have 2 names. I just want to have a unique set of 4 numbers that represents that orientation. So that's what we're going to see on Wednesday. So we'll catch you then. One more day.